So if you think of a representative TMT-based experimental workflow, what we typically have is, for instance, if you have 3 controls and the 3, I put a difference here, there is some difference with respect to the control. It can be a genotypic change or a drug treatment here. And cell lysis, we do proteolytic digestion, we label them with these TMT labels mixed together, and we do fractionation offline, and we then do LC-MS analysis to get identities and the T quantification levels. So as you could see, there are many places that you can have systematic errors, and sometimes they are unavoidable. For instance, if you start lysing the same amount of cells, there will be differences in total protein amounts that you get from one sample to the other. And there also can be significant peptide abundances after doing the digestion and then doing the cleanup of the samples. And there can be have differences in labeling efficiency. So these systematic errors can be traced back, and we can basically minimize them by, for instance, adjusting the protein amounts. For instance, suppose you have 2 milligrams here, 2.5 here, and 1.5 here. And so we will use the minimum amount, and basically we correct and normalize according to, so that we have the same amount across all the samples. And also you can change reaction times if you are not sure the kinetics and the thermodynamics of the labeling is properly accounted. So those are systematic errors, and those things can be minimized. And random errors is coming from, for instance, for unknown reasons, and we are unable to track, or we don't know where the errors are happening. So these basically can be corrected or minimized by statistics, for example, normalization. So how we go about it is, after doing all these possible corrections to the workflow, at the end, what we see is the TMT responses of many peptides, 30,000 to 70,000 peptide identity quantifications we have. So we look at the total addition of these responses that we get out of those many MSMS profiles. So before normalization, in this particular experiment, this is a real experiment we had. As you could see, the abundance, the mean value is changing from one sample to the other for different labels. So why this variability is there, we actually do not know. It can be during the fragmentation, it can be anything. So this kind of variability is not very significant variability. If they are like one to have like significant variability, if you see a very significant variability, that means the data set is not in good form to be utilized. But this variability is not that high, so that we can basically correct them by changing each of the identities and coming into a medium value or a mean value of these values that you obtain here, and correcting them. So after correcting them, then you will have, for each peptide, there will be quantifiable intensities taken into consideration. So these are some little bit details that I wanted to emphasize how we go about doing a quantitative proteomics workflow in procedural errors. Yes,
Aruna.
Yes.
And so I could mention that this type of normalization method is very similar to what's done for RNA sequencing and high throughput sequencing. Okay. So it's also a normalization. In those cases, it's typically done by the total read count. Okay. And that's similar to what's being done here, although it's not, I believe it's intensity though, in this case, the abundance value rather than count. And so then again, it's based on the ion abundance, yes, rather just than the number of times that you've seen it. So it's actually a more, it's a different type of analytical measurement. So,
yes.
Yeah.
Thanks.
But the normalization is the same.
Same.
Or similar.
Similar.